We have two more sections to discuss in this course, and they deal with integrals using the substitution method for definite and indefinite integrals. This one, we're going to look at substitutions of the traditional ones of finding areas between curves in the x-axis and within a bound. And the next one is just finding the areas between two separate functions in anywhere in three-dimensional space, or two-dimensional space, not three-dimensional. So let's begin. Section 5, definite integrals and the substitution method. We use the substitution method, second derivative, second the chain rule. It makes it much easier for us to solve these things. Important note, by the fundamental theorem of calculus, any definite integral of a continuous function can be found directly if we find not the an antiderivative of the function. The reason it's an antiderivative, because you can have any two antiderivatives will differ from each other by a constant. We talked about this in chapter 3. If I asked you, find me a function whose derivative is cosine, what would you tell me the answer would be? What? If I asked you for a function whose derivative is cosine, it would be sine. That's one formula. Could it be sine plus 3? Sine minus, so it's sine plus or minus some constant. So there are an infinite number of different possibilities we can have here. So that's what's happening here. Is whenever we take the integral of a function, it equals the solution. It's back to the original function plus some constant. This is an example of an indefinite integral. Can you guess why it's an indefinite integral? As opposed to a definite integral.
There's no bounds.
Very good. There are no bounds. There doesn't go A to B. So that's the reason when you do take an integral of a function without giving bounds, you don't come up with a solution, you come up with an equation with a constant in it. So the integral of a function indefinitely will give you a function like this. This, on the other hand, a definite integral will always end up with a number. This out of there. All right, so let's look at this. We're talking about substitution method. The substitution method, okay, integrals are really just the derivative going backwards. So what this is going to look at, we're going to do substitutions using the chain rule in reverse. Let's review. If my function was u to the power n, what would be my derivative? du. You can't forget the du part. Because it's going to be important. Du is a function of x. Remember, the function itself is a function of x. So it's going to be backwards. So if we had the derivative with respect to x of u n plus 1 over n plus 1, what would that equal? If we took a derivative of this, what would that equal? Bring the n plus 1 down. So what you'll have is n plus 1. And the top it's n plus 1 minus 1 all over n plus 1 du. So the n plus 1s cancel. We're left with, and the 1s would cancel. So we're left with u to the power n du. Du dx. Remember, it's a function of x. So that's the derivative. If this if the derivative of u n to the power n plus 1 over n plus 1 is u to the n du dx, then the integral of u to the n du would be what? Or du dx would be what? We just finished talking about that. If this is your derivative, if that's your derivative, then the integral would bring us back to what the derivative, so this one brings us back to there. Because the integral is the backwards of a derivative. So if that's the derivative of this function, then the integral of that is the original function. So basically, what does it tell you? If I asked for the derivative or integral of x to the 5th dx, what would that give me? Using this formula, what would that give me? It'd give me u n plus 1, so it's 5 plus 1 over 5 plus 1 plus c. So it gives me u to the 6th over 6 plus c. You see the formula we're getting to when we do integrals of exponentiated terms. If this is my term, it should be x, I'm sorry. It should be x, not u. Because this exponent, since this is the derivative, it had to come from where? Well, it had to come from someplace that's one bigger earlier. Because I bring that down. Well, since it's no longer there in front of you, I have to divide by it. So that's a general rule when we deal with integrals. This right here.
What would you have to do
Whatever the exponent is, divide by it, add one to the exponent, and then divide by it.
Would you have to
Plus-
do quotient on the bottom? Like if you have x to 6th over 6th, or would it the unit power rule and the sixes cancel?
For the derivative,
Yes, sir.
no, there's no this. You're doing the integral of it. We're setting up the equation, like I just said right here. Well, if my function was x to the 6th, what would the derivative be? How would I get x to the 5th as my derivative? The derivative of x to the 6th is 6x to the 5th. But the 6 is missing, so I have to divide by 6.
Oh, okay. Thank you.
So as long as these two are the same, I take the derivative, it disappears. And that's why we're going backwards. We have to have one on top and bottom. All right, let's look at an example here. Note, also note, we know that du dx is equal to du dx, correct? Yes. If we multiply both sides by dx, we get this. This will become more important in a second. We'll do the example. Remember, we're using substitution rule also. When using substitution, the hardest part is figuring out what is my u. You have three different parts here. You have x cubed plus x, you have this parenthesis raised to the 5th, or you have 3x squared plus 1. So what is your u? Because whatever you pick, you have to make sure that you have a corresponding du in there as well. So typically, it's always the highest exponent inside the parentheses is your u. In other words, this one. Why is that? Because when you take the derivative of it, you have to make sure that the du part is in your equation. So if I said this first part is my u, so I have u to the 5th, and my du is this whole part. That's the reason I went through this. To find du, the du dx, you have to have the derivative of it with a dx behind it. The derivative of the inside is that with a dx behind it. Now, all we have to do is take the integral of this equation, this part right here. So what is the integral of u to the 5th? U to the 6 over 6 plus c. If you're not sure, try it. Then take the derivative of this. It should equal that. That's why it's not u to the 4th over 4. If it was u to the fourth over 4, and I took a derivative of it, I would have u to the third. I'm going the wrong direction. So whenever you take the integral, your final answer has to be a higher exponent. We're not done yet because now we have to put everything back. U is equal to x cubed plus x to the 6th power over 6 plus c. And there's my solution. Example 2. Evaluate this one. So we have to define a u, then we have to find a du. That's right in front of the dx. So what's our u going to be? Because this equation, we can now rewrite it as u to the power 1/2 dx. If we left it as a square root, then we have a much more complex du. Because remember, du is supposed to be whatever is in front of dx. So what is my du? 2 dx. But there seems to be a problem. What's missing in our equation here? We're missing a 2. We have the square root of 2x minus 1, but for our du, we're missing the 2. So we can put it in there. But whatever we put in there, we have to divide by it out in front. How does that work? Because remember the rules of constant multiples? If we have a constant multiple in there, we can bring it out in front. Then we have 2 over 2. What is 2 over 2? 1. Nothing's changed. So if we're missing a constant value, we can plug it in there. But whatever we plug in there, we also have to do the reciprocal of it out in front. So what we have here is now it's all set up. So our u was defined as 2x plus 1. The du is 2 dx. We have everything we need. So what does this give us? This gives us u to the power 1/2 du. There's our u to the power 1/2. So what's the integral? What do we do for the integral? There's the 1/2 out in front. What's the integral of u to the power 1/2? So it's 1/2 plus 1 over 1/2 plus 1, which is 1/2 u to the power 3/2 over 3/2. Yeah, but we're not done with this part yet, but we'll put plus at the end. Okay, so we have 1/2. Take this, since it's a fraction, reciprocate it. U to the power 3/2 The 2's cancel. So we have 1/3 u to the power 3/2 plus c. Are we done? No, because we have to put it back into our terms of x. So the final answer is going to be 2x plus 1 to the 3/2 power divided by 3 plus c. There's my answer. Theorem 6. The substitution rule. If our substitution, if we set u to be the function g of x, is a differentiable function, and whose range is some interval, and if f of x, another function, is continuous on that interval, okay, what does differentiable mean? So whatever we set, whatever our g of x, we can use that as long as we could take a derivative of it. If it's not differentiable, which means it's continuous, if it's not continuous, then we can't use it. We have to use something else on that interval. So then if all that's true, then what we have, and we've seen this formula before, the composite function f of g of x times the derivative of the inside, and that equals f of u du. It's kind of like the chain rule. We have the outside function, take the derivative of the inside function. Remember, if u is g of x, then g prime would be u prime, which is du. Let's look at an example here. Secant squared 5x plus 1 times 5 dx. Okay, these are easily set up. What you could have been given is this. Or you could have been given this. Why is this one easier to work with? Because once we define our u, what is our u? What's the innermost function? So du would be 5 dx. which is right there. So once you define these and find du, we could look at it. So now we know that we're set up as secant squared of u du. Everything's good to go. But what if I gave you this? You would say, well, where's 5 dx? Or if I gave you this, where's the 5 dx? Do I have to put it in there? No, because it's already there. So you have to be able to view it and apply it as you see fit. So what's the integral of secant squared? So remember, this is the derivative. What function has the derivative of secant squared? Tangent. So it's tangent u plus c. And now we could go back. U is 5x plus 1 plus c. The question you would ask is it always going to be plus c? Yes, unless we have what's called an initial condition. Unless we say that this function has to go through a specific point, then we know what has to equal. So we plug in the x value of that point, plug it in there, we know what equals y, and then we solve for c that way. So if we're given more information, then we could, if we can solve for the value of c, we do it. If not, it's always going to stay that way. It's going to be a plus c. Example 4. The integral of cosine 7 theta plus 3 d theta. So we set up our u. What is our u? What's our du? Seven dx. So what's missing? The 7. So we can put a 7 there. If we put a 7 inside there, what do we have to put outside? 1 over 7.
How did we know we needed to put a 7 there?
This derivative, if u is 7 theta plus 3, then du is the derivative of this is 7.
Oh, okay. And so sometimes it won't, that du on the initial integral we're given, it won't be,
It won't have it in there, right?
Okay.
Yeah, because we're going to look at different scenarios. We're going to see this missing a number. We can put a number in there. That's the easy part. The harder part comes if you have an extra x value in there. So right now, yeah, if you're missing it, just a solid number, just plug it in there. Whatever you put in there, you put the reciprocal out in front. So we have integral of cosine of u du. What is the integral of cosine? Sine u plus c. And then u is 7 theta plus 3. All that plus c. So there's my answer. What if an extra x is in the integrand. That is one less than the x that's in the argument of the function. This one, where's that example? Oh, well, here's the example. X squared e to the power x cubed dx. So we have to figure out what is our u. You have an x cubed here and an x squared here. What's our u going to be? No, that's an exponent. This is a coefficient. You only add them as if you're multiplied together. Always use for the u, use the higher exponent. The reason for that is because our du will have to be what? It'll be one smaller than it. So it's the derivative of it. And it's one smaller. So here we have our x3. So we're going to rewrite this equation. It'll be e to the power u. And here's x squared. But it's missing a what? It's missing a 3. So we give a 3 du. So since we put a 3 in there, we have to put a 1/3 out in front. So it's 1/3. What's the integral of EU? Plus C. That's it, since that's right there. It makes it much easier looking at it that way. So when we put everything back, so that's if you have two variables with different exponents.
So what would happen to that x squared? Like, how is that able to disappear?
Because this x squared is really going to be over here. So if u is equal to x cubed, then du is equal to 3x squared dx, which is what that is. So this becomes EU du.
Okay.
But since I'm missing a 3, I have to put one in there. So that's if you have different powers of x. Now, that's the difference of only 1. If it was greater than 1, then in calculus 2, you're going to learn another method where we have to repeatedly do a process until it becomes equal. What if an extra x appears? in the integrand. The integrand is whatever's after the absolute value, I mean the radical symbol, not radical, the integral symbol. Example 6. So here's our example. The last example, we had two x's, but they had different exponents. One was higher than the other. This one here would be higher than this one. Now, if they're both the same, how do we go about solving this one? Well, first off, we have to define our u and find our du. Our u is going to be what? Our u is always inside the function. Remember, we define u as g of x, which is the inside function. In theorem 3, g of x is what we define u as. It's the interior function. Again, as I told you earlier, the theorems dictate everything. We have a function within a function. We have a function within a function. So u is going to be the interior function. What's our du going to be? To dx. Okay, we have a problem automatically. Do we have a 2 in there anywhere? No, so we have to put a 2 in there, and that means we got to put a 1/2 out in front. If I'm taking the integral and I have a constant coefficient, I could take this number and put it out in front. Now, but that's just because it belongs there. If I put this in there, did it change the equation? So if I started now, if I just put a 3 here, and it's supposed to be x squared, is it still the same? How would I make it the same? If I multiply by 1/3. Because remember, this 3 can come out in front. So 3 over 3 is what? 1. I haven't changed anything. All I did is change the way it looks. All right. So so far we set it up. And we have this right now. Because this is our du. This is our u. And this is, but what, again, we have an x. When that happens, go back to this one where you set for u and solve for x. So since u is equal to 2x plus 1, solve for x. So we have u minus 1 equals 2x. X is equal to u minus 1 over 2. So I have u minus 1 over 2. And I have u to the power 1/2 du. Now I only have an integral and the integrands are all just functions of u, no more x's. Okay, algebraically, what do we do? Well, this is a constant multiple. This one half on the bottom, I could bring it out on top. Or in front of me. Because it's a constant multiple, I could bring it out in the foreground, in front of the interval. Which makes it 1/4 now. Inside here, I could distribute. So u to the first times u to the 1/2 is u to the 3/2 minus u to the power 1/2 du. Now I can take both of those separately. How do I do that? So what's the integral of the first one going to be? It's going to be u to the 3/2 plus 1 divided by 3/2 plus 1 minus u to the power 1/2 plus 1 divided by 1/2 plus 1. All that plus c. Three over 2 plus 1 is 2/2 is u to the 5/2 over 5/2 minus 1/2 plus 2/2 is 3/2 over 3/2. Which is equal to 1/4. Since this is a denominator, I can take it and reciprocate it. So it comes 2/5 u to the 5/2 minus 2/3 u to the power 3/2 plus c. Distribute the 1/4. So we have 1/4 times 2/5 u to the 5/2. 1/4 times 2/3 u to the 3/2 plus c. The 2 and the 4 cancel. So I have 1/10 u to the 5/2. The 2 and the 4 cancel. So I have 1/6 u to the 3/2 plus c. So u was 2x plus 1. So I have 2x plus 1 to the power 5/2 over 10 minus 2x plus 1 to the 3/2 power over 6 plus c, and there's my answer. So if your exponents are not the same on your variables, then we'll take the derivative of the inside one. If you have an extra x, take your substitution and solve for x, and then plug it in there. Example 7. This is an example of using trigonometric identities. So for the first one, we have integral of sine squared x dx. We don't really have an integral for sine squared. We have it for sine x squared dx, but we don't have it for sine squared dx, x dx. So, using trigonometric substitutions, what substitution do we have for sine squared x? That's where I gave you the cheat sheet, so you can look in there. Because we want to look for one that doesn't have any exponents and that's easily integrable or derivatable, differentiable. Look for identities for sine squared. Which would be what? Very good. Very good. Because now we have no more squares, no more exponents. We're good to go. Because this is an easier one to take care of. One minus cosine 2x over 2 dx. Reason this is easier because this one we can separate everything. So that denominator comes out, and that comes outside the integral. So we have a coefficient of 1/2. We could do the difference rule for the integrals. Take the integral of 1 dx minus the integral of cosine 2 dx. Or we could leave it like this and treat it all as one equation. Let's do it both separately. So we're taking the integral of 1 dx minus the integral of cosine 2x dx. What's the integral of 1 dx? X. Minus, what's the integral of cosine 2x? Well, to do this one, what do we need to have? We have a function within a function, so we define u as being what? 2x. What is du? 2 dx. So what are we missing in this one? We're missing the extra 2 in front of the dx. So we have to put a 1/2 out in front. So it gives us 1/2 integral of cosine u du. 1/2 x minus 1/2. What is the integral of cosine u? Sine u. All this plus c. Distribute that 1/2 in front. So we get x over 2 minus 1/2 times 1/2 is 1/4. So it's sine u over 4 plus c. And u was defined as 2x. So it's x over 2 minus sine 2x over 4 plus c. See, and that's also the bad part about just copying, Xeroxing what I put here. If anything doesn't make sense, you should be asking questions instead of waiting to get home and get lost. Whereas if you couldn't do this stuff without me walking you through it, then you should ask those questions. How did you get that? Why did you get that? Where did you get this? B. Look at cosine squared x dx. Again, we have integral of cosine squared. What is the identity for cosine squared? Two x is just 2. Well, no, it's 2. It's 2 theta, right? Right. It's in the trig identities, not the calculus derivatives. Again, that's right. In this course, you have to know algebra and you have to know trig. Then the calculus part's just easy to plug and play. So this is 1 plus cosine 2x over 2 dx. The 1/2 comes out in front. So I have 1 plus cosine 2x dx.
How are you able to get that 1 inside if you already took the 1/2 out?
What do you mean?
Where you changed 1 plus cosine 2x over 2 to, you brought the 1/2 out, the constant. So shouldn't it be cosine 2x instead of 1 plus?
Yep. Because the top is still the top. All I did was factor out the bottom part. The same thing I did the last question. Since this is a fraction, I can bring the fraction out in front. This constant could go out in the whole thing.
Oh, so there's a constant outside of that original 1 plus cosine 2x?
No, there's nothing in front of it. But no, it's what this equation can be written as is 1/2 times 1 plus cosine 2x.
Oh, okay.
Any fraction can be taken out.
Okay, I was thinking that 1 in front of that plus sign was a part of that 1/2.
No, it's the numerator. It's a whole numerator.
Okay.
The whole thing is divided by 2. So the integral of 1 dx plus the integral of cosine 2x dx integral of 1 is x. For this one, we have a function within a function, so it's u is 2x, so du is 2 dx. We're missing a 2 in front of the dx, so I put a 1/2 out in front. So now it's cosine u du. So it's x plus 1/2. The integral of cosine is sine of u. Distribute there. One half times 1/2 is 1/4. And plug our 2x back in place of u. Okay, I see what you were getting at. Because it was 1 plus 2 cosine. You thought that was that 1/2 plus cosine 2x. No, it's the whole equations on top of there. Right. Third one says tangent u du. Integral of tangent x dx. For this one, we can break it down to sine x over cosine x. We could set u as cosine x and du as negative sine x. Because if we set sine as being u, then du would be on the bottom. We don't want that. Because what we need is we need to have sine something with a dx in front of it, not a 1 over cosine. So very good question. It's just that it makes it much easier doing it that way. So what we have now, we have du over u. So what's the integral of du over u? That's the ln function.
I'm thinking e from u is the negative sine x over cosine.
It is. So the integral of 1 over u du. What function gives me this as a derivative? 1 over x. Yeah, which is ln u. So it's ln, but u is negative. Du is negative. So it's the negative absolute value of u. Because du is negative, so it comes out in front. Plus c, since we took the integral. So we have negative ln absolute value of cosine of x. Why do we need the absolute value around cosine of x? No, why do we need the absolute value? What's the limitations of ln? Has to be greater than 0. You cannot take the ln of a negative number or 0. So that's why we take the absolute value of it. Are we done? No. Because whenever in logarithmic equations, whenever you have a coefficient, that coefficient becomes an exponent. It goes on top. The rule says this: ln of x to the power n is n ln x. That's the property of logarithms. Since we have a -1 coefficient, it becomes a -1 exponent. Which means what is 1 over cosine? So it's the absolute value of secant of x. That's my answer. So what's the difficult part about so far? Besides everything. Because what you're trying to do is, the last 3 examples we just did, take a quadratic equation and put it into a linear function. In other words, rewrite them so you don't have any more exponents. That's what we did with the identities of the trig functions. With the tangent function, it's much easier dealing with sine and cosine, and we can find the derivatives of those much easier. And besides that, what function has a derivative of tangent? You won't find one. So that's why we have to go to this other route to get the ln function of the secant. So the last example was using trigonometric manipulations, identities. Now let's look at algebraic manipulations. The integral of dx e to the power x plus e to the negative x. We're going to look at both of these. The integral of secant x dx. How many of them are there? Yeah, almost done. This also looks like 1 over e to the x plus e to the negative x dx. The difficult part about this one is look at the denominator. It's got a negative exponent. That's what it really looks like. So what we could do, we can go ahead and rework all this stuff out, get a common denominator, add the bottom one. So what do you get? So get a common denominator down here. What do we do? Yeah, the first one is over 1. So it needs e to the x over e to the x. So we have e to the 2x over e to the x plus 1 over e to the x. So it's e to the 2x plus 1 over e to the x. We have a fraction over a fraction. So leave the top fraction, leave it alone, which is a 1. Flip the bottom, we get e to the x, e squared x plus 1. Any questions so far? So now our substitution is going to be what? What's our u going to be? E to the x. What is that going to give us? So we have,
Shouldn't that be e to the 2x because that's the greater exponent for the u?
Right.
e to the 2x is e to the x squared. So we have a function down here squared plus 1. We want that because if we look at our equations, is there an integral of x squared plus 1? Or what equation? Is there an equation whose derivative gives us 1 over x squared plus 1? No. Look again on your sheets. Is there a function whose derivative gives us 1 over x squared plus 1? The inverse tangent. So it's inverse tangent of u plus c, which is the inverse tangent of e to the power x plus c. Be religious using those cheat sheets. Because if I've made this bottom one e u, it makes it u squared. U squared plus 1. The du is on the very top. That makes it, because we need du, we need ex dx, which is why the top part is du. That was a kind of a messy one, but you have to be very careful on how you do these. So algebraically, we just fixed the bottom, simplified it, got it to this point. Highest exponent is 2x. That's highest exponent because it's e to the x squared. So u is ex derivative ex dx, which is what's on the top. All right, secant.
One of, you, you times the ex,
What's that?
because like you multiply, so e of x, e to the power of x, that was our e.
There's our u.
And when you multiply that with dx, it became du.
Well, u is e to the power x. Du is a derivative of this, which is ex dx.
Ex times
Right. Yes, yes. E to the x times dx is du. Because whenever you take a derivative of du, remember, u is a function of x. You have to put a dx behind it. That's how we started off the whole discussion today. Where is that? because we needed to have G prime, which is du dx. So G prime dx gives us du. So whenever you take a derivative of u, it's got to be a function of x. This one's going to be a little bit more difficult to guess what we have to do next. So if we said our u was x, du would be 1 dx, which we have there. But what is 1? Now, why would someone, what's the derivative, or what's the derivative of secant? Secant x tangent it. Secant x plus tangent it, or secant times? So because of that, it's not an easy transformation. So what are we missing? What we're missing is that is our 1. That's what we're going to multiply by. Because you're right, we have secant tangent x. We have to get rid of those. Remember, this is the derivative. We need to know where did it come from. Secant x So that gives us secant squared x plus secant x tangent x all over secant x plus tangent x. What what do you think our u is going to be? Is it going to be this whole thing or this whole thing? Because if we call this u, what's the derivative of secant? What's the derivative of tangent? And we add those together. So our u is going to be our denominator. Because then if we take our du, what's the derivative of secant? From your sheets. Plus, what's the derivative of tangent x? You see how this looks a lot like that? So it's all that dx. So what we have now is du over u. So what's the integral of du over u? Or integral of 1 over u du? ln absolute value of u plus c. So we have ln u is secant x plus tangent x plus c. That one was a lot more difficult to follow. But whenever you deal with secant functions, you're always looking at some combination of secant and tangent, because the derivative of secant is secant tangent. So we're looking for some sort of combination of that. I'm going to call these, I'm going to give you these, I call these the rational trig functions. The integral of tangent, I call that, it's irrational because it's sine over cosine. And we saw this one earlier as ln secant x, absolute value secant x plus c. That's the first one. The integral of secant x dx. We just did that one. Because both of these we just did earlier as examples. So tangent one, now we look at cotangent. The inverse of cotangent is sine x, or ln absolute value sine x. Cosecant x dx is just the opposite of the secant. So it's negative. Instead of secant, it's cosecant. Instead of tangent, it's cotangent. So these are just the ones that make it much easier for us in the future. What if we had this monstrosity? So what's our u going to be? And what's our du going to be? The interior function, yep, x squared plus 1. Two x dx. So we have 2x dx, that works. So this can be rewritten as u to the power negative 1/3 du. Because here you have 2x dx, that's my du, and I can bring that one up on top. So the integral of -1/3 is -1/3 plus 1, which is plus 3/3. -1/3 plus 1, which is 3/3, plus c. Which is u to the power 2/3 over 2/3. We'll worry about plus c later. Take the reciprocal of the bottom, so it's 3/2 u to the power 2/3. Three over 2 x squared plus 1 to the power 2/3 plus c. And there's your answer. All right, this section we looked at only indefinite integrals of the trig functions. Not only the trig functions, but it's using substitution. The last chapter, which we'll cover on Monday, the last section will deal with definite integrals, because whenever we use substitution, we have one of two options we can do. If you use definite integrals and you use substitution, you can do the integrals. But if you leave it as the u function in substitution, then you have to change the bounds of integration. Or it's right here. If this was going from 1 to 3, let's say this was going from 1 to 3, and I left it in terms of u, and I did the whole thing, then I would have to change my bounds of integration, because now I'm taking the integrals with respect to u, du, not x. So I'd plug in 1 for here. So my lower bound would be 1 plus is 2. This is 3, so it's 9 plus 1 is 10. If I'm going to keep it in the form of du and u, then I have to change the bounds of integration. If I want to go back to the x's, I do all this stuff, and then I put 1 and 3 back in there. That's what we're going to do next time. And I'll show you what it means in detail. And that'll be it for the course after we finish that.